Hello, everyone. As the eyes of machine vision, the type and performance of lenses are crucial. So, what are the characteristics of the different types of industrial lenses? And how do performance parameters affect image quality? Let us embark on today's learning journey with these questions in mind. This lesson will mainly cover the following two topics. It is hoped that through this lesson, you will achieve the following objectives. First, let's understand what an industrial lens is. An industrial lens is a lens specifically designed and manufactured for industrial application scenarios. It is an important component of a machine vision system that directly affects the effective image resolution, image clarity, and image distortion of the vision system. Therefore, selecting the appropriate industrial lens is a key step in building a machine vision system. Next, let us look at the classification of industrial lenses. Based on focal length, they are divided into zoom lenses and fixed focus lenses. Based on aperture, they are divided into variable aperture lenses and fixed aperture lenses. Based on magnification, they are divided into fixed magnification lenses and variable magnification lenses. Based on application, they are divided into FA lenses, telecentric lenses, and microscopic lenses. FA lenses refer to standard factory automation lenses. They are industrial lenses designed according to general optical imaging principles and are also known as standard lenses. FA lenses are generally of fixed focal length with an adjustable aperture. The lens is equipped with an aperture adjustment ring and a focus adjustment ring. The purpose of the aperture adjustment ring is to change the size of the lens aperture. The purpose of the focus ring is to adjust the relative position between the camera sensor and the focal plane to ensure clear imaging. FA lens interfaces mostly use threaded C or CS interfaces. Telecentric lenses are designed to correct parallax in traditional industrial lenses and maintain a constant image magnification over a given range of object distances. Due to the parallel optical path design of telecentric lenses within their telecentric range, changing the distance between the lens and the object does not change the size of the image formed. In contrast, with FA lenses, the closer the lens is to the subject, the larger the image produced. Having understood the types of industrial lenses, let us now study the performance parameters of industrial lenses. There are mainly 9 items. 1. Focal length. A camera lens is a group of lenses. When light rays parallel to the main optical axis pass through the lens assembly, they converge to a point called the focus, and the distance from the focus to the optical center is called the focal length. The clearest image formed by the lens is generally located slightly behind the focus. Focal length is an important performance indicator that determines the image size, field of view, depth of field, and perspective strength. 2. Aperture f-value. This refers to the ratio obtained by dividing the focal length by the diameter of the lens's aperture. In other words, the f-value is calculated as f-value equals focal length divided by aperture diameter. For example, a marking of 1 to 2.8 on the lens indicates an aperture f-value, which can also be written as f2.8. For the same focal length, a larger aperture allows more light to reach the camera sensor. For the same aperture size, a shorter focal length permits more light to reach the camera sensor. 3. Depth of field. There is a certain range of space in front of and behind the object side focal point of the lens. When the subject is positioned within this range, Its image on the image sensor remains within the permissible circle of confusion. This range is called the depth of field. Depth of field varies with the aperture value, focal length, and shooting distance. A larger aperture produces a shallower depth of field, whereas a smaller aperture yields a deeper depth of field. Similarly, a longer focal length results in a shallower depth of field, and a shorter focal length results in a deeper depth of field. The closer the shooting distance, the shallower the depth of field, while a greater distance produces a deeper depth of field. 4. Working distance. This is defined as the distance from the front end of the lens to the subject when the lens is capable of producing a clear image. When selecting a lens, it is essential to consider whether the installation distance permitted by the sight environment falls within the lens's acceptable working distance range. 5. Field of view angle. Taking the lens as the vertex, the angle formed by the two extreme edges of the image of the target that can pass through the lens is called the field of view. The size of the field of view determines the extent of the visible area. The larger the field of view, the larger the visible area, and the lower the optical magnification. The focal length of the lens defines its field of view. The relationship between the field of view and the focal length can be approximately calculated using a specific formula. 6. Viewing field. The viewing field of an industrial lens refers to the range within which the lens can produce a clear image. This is directly related to the lens's working distance and its field of view. When selecting a lens, the viewing field must be larger than the size of the object being imaged. 7. Distortion. Lens distortion refers to the phenomenon where inherent perspective errors in an optical lens cause the actual image to differ from the subject. Distortion is very detrimental to machine vision imaging. Pincushion distortion and barrel distortion are common. Pincushion distortion results in the image contracting toward the center, whereas barrel distortion causes the image to expand in a barrel shape due to the physical characteristics of the lens elements and the lens group structure. The degree of optical distortion can be expressed as a percentage, calculated using a specific formula as shown here. 8. Maximum compatible sensor size. Each industrial lens is only compatible with cameras whose sensor sizes do not exceed a certain limit. To ensure full utilization of the camera sensor and overall image quality, the maximum compatible sensor size of an industrial lens should not be smaller than the sensor size for which it is intended. 9. Resolution. This describes the lens's ability to resolve details. Specifically, it refers to the number of alternating black and white line pairs per millimeter that can be resolved on the imaging plane, measured in line pairs per millimeter. Although the lens itself does not have a resolution parameter, product advertisements often describe megapixel industrial lenses or 5 megapixel industrial lenses. In fact, these descriptions refer to the maximum resolution of an industrial camera that the lens can support. This parameter is provided by manufacturers based on the lens's resolving power, roughly recommending the camera resolution that should be paired with the lens. Everyone, today's mini lecture is coming to an end. In this lesson, we not only gained an in-depth understanding of industrial cameras, but also thoroughly discussed their performance parameters. We hope that you will apply the knowledge you have learned in practice and contribute your strength toward building a robust nation in intelligent manufacturing. Let us remain true to our original aspirations and forge ahead with determination. This mini lecture concludes here. Thank you, everyone.